Now let's take a look at what really is an interest point in an image. Let's take a look at this object right here and two images of it taken under different conditions. If you consider this patch right here, this local area, you see that there is a difference in size because the magnification used is different in these two cases. There's of course a difference in orientation, in lighting for sure, perhaps the distribution of light, but also the intensity of light, and so on. So any interest point detector that we want to develop should be able to compensate for or remove for these variations. Only then can it match a feature in one image to a feature in another image. And so if you consider this patch that we were looking at earlier, you see the differences right here. We want to be able to somehow normalize or compensate for scale differences. Rescale one so it matches the scale of the other. We want to be able to reorient one so it matches the orientation of the other. And we also want it to be more or less insensitive to brightness and lighting changes as well. So in other words, matching features or interest points becomes easier if we can remove variations such as size and orientation. And when you develop an interest point detector, you also don't want it to respond to a lot of things in the image. There are a lot of patches in an image that are simply not interesting. There is stuff going on here, but it's not unique and interesting enough to actually detect and use for matching purposes. So all that said, what are the desirable attributes of an interesting point or feature? Well, first, an interesting point has to have some rich image content around it. The local appearance around this point should be rich enough in terms of brightness variations, color variations, etc., that there is a certain amount of uniqueness to it that can be exploited for matching purposes. Second, it should have a well-defined representation. What that means is that from this appearance in this local window, we should be able to compute a signature that we can then use for matching purposes. And it has to have a well-defined position because ultimately when you recognize things, you also typically want to know where they are. So position is very important. It has to have a well-defined position in the image. It should be invariant to image rotation and scaling. So if you want to find things under arbitrary rotations and scales, the interest point itself should be able to produce a signature that finally is invariant to image rotation and scaling. And finally, it should be insensitive to things like lighting, as we mentioned before. So all this said, with this list of desirable attributes, the question again is, what then would be a good interest point? So first question, the obvious one, are lines and edges good interest points? Well, let's take a look at that. Here you have an edge in this image. This is an image of a scene. This is a slightly more close-up image of the same scene. And here you have an edge here, and we already know that edges are rapid changes in brightness within a small window, and that's what you see here. You have a rapid change. And the question is this interesting enough? And unfortunately not, because when you look at this image, you're going to see lots of edges there that have the same kind of brightness variation. And so the problem with edges is that edges really slide along boundaries of objects and they look pretty much the same as they slide. They're not really descriptive enough and unique enough to be used as interest points. Now, this might lead you to believe that perhaps corners are good. And indeed, corners are interesting interest points, and they have been used as interest points in the past, but for simpler applications, not for recognizing complex objects, because corners just don't show up that often and by themselves are not very unique features. So now let's take a look at something else, which is blobs. So here you have a region in this image, right here, this blob, and here is the same blob in this image. And after you normalize for scale and you put them in windows of similar size, they look like this. And what's interesting here is that you have some kind of a local appearance in that there's brightness variation going on in here. and that defines the appearance of the blob itself, and also the position of the blob is very well defined. So yes, blobs have a fixed position and may have some interesting appearance within it, and therefore could be potentially very good interest points. So we're going to do exactly that. We're going to use blobs as interest points. And so for a blob-like feature to be useful, we needed to have certain attributes. First, we need to be able to locate the blob. That is, there should be a position associated with it. The position doesn't have anything to do necessarily with any particular feature in here, inside the patch. It is a position that emerges from the way we actually do the detection of blobs. And then it has to have a size associated with it. Size, again, is a very interesting concept in this case. It has nothing to do with edges or boundaries of the appearances or the various visual artifacts that you see inside of the blob. It's just the rough scale of this appearance itself. It's a fairly abstract concept in this case, the size of the blob. And then you have, of course, an orientation associated with the blob, because the blob itself can appear in different orientations, so we need to be able to compute a principal orientation of the blob. And finally, we need to be able to, after we have done all of this, extract a description or a signature which relates to the appearance inside the blob itself. This signature is very important for matching purposes, as we mentioned earlier.